Engineering 305, Chapter 5, Section 6, Stress Concentrations. This is a good one. The course learning objective that we have is to evaluate the stress concentrations from various geometric features. The equation from the study guide that relates to this topic is that the stress, which has always been equal to the force over an area, whether that's P or F, now gets this modifying factor, K. And the goal of this section is to help us find K for a variety of geometric considerations. Essentially what we're talking about is, and I got to start drawing pictures, if I have a bar that is straight and I pull on that like that, then what we've always talked about is an average stress distribution. So that if I cut it in the 3-dimension, what we get is all across that, I get a uniform stress distribution as that bar gets yanked. And if I just do the 2-dimension, what you would see is there's my line, and at every location I pull up. Now, let's go to the next slide and we'll start saying, okay, well, so what's a stress concentration? Well, if I have a plate, same plate with a hole in it, well, if I draw that line here and then start putting in my stresses, you would say, well, yeah, I've got uniform stresses there. And if I drew another line where the hole is, you would say I've got uniform stresses there. And this stress, the blue stress, is equal to, what do I got, load P or load F? We got to decide. P over A, and down here for the red, I've got this P over A. But now these stresses aren't the same. This area is smaller. So therefore, this stress is higher. So if I would redraw this, let's put my hole back in the plate. And now when I draw this, these have to be longer. Okay, that makes sense, fine. But let's go one step farther. Let's segment my plate like this. And let's say that all my stresses have to play in their lane. Well, if the stresses don't shift left and right, then where does that stress go? And that becomes the problem. How do I shift these stresses left and right and figure this out? Well, let's talk about how this actually works, because it doesn't work like blue and it doesn't work like red. Far away from the hole, it does work like the blue, that we get some average stress. And you saw this in the FEA problem that you did. But it doesn't work like red. The red line is inaccurate. If I have a plate and I put a hole in it, yes, at some distance away, oh, and I'm going to pull on it. I'm going to pull on it with a force P. I do get some average distribution, which the stress is equal to P over A. And that worked pretty well. But close to the hole, this stress has to adjust. And so I get stresses that are high right next to the hole. And then they decrease. And that's the actual stress distribution that I get. So what we've learned about as we've tested a variety of bars and a variety of situations over a long period of time, what we've learned is that the amount this increases is dependent on the geometry. It's dependent on the variables that start to come into play are this width and that diameter. And we can start making some correction factors to this equation that take that into account. And so we have generated, we've been using historically, stress is equal to K times P over A, or force. I'll put that, or F, because we've been using F over A. But that K is now just a correction factor. And that works pretty well. So the key for this section in the text is now what kinds of situations do we face, and how do we find the correction factors? Well, the situations that we face look like a plate with a hole, or, oh, I can't do that because I can't erase. A plate with a notch on the sides, or a plate that has a step in as it's being pulled. Now, one of the things we have to worry about is this could be a plate like this, right? Or it could have been axisymmetric, such that it was two rods. It could have been a wedding cake problem, or a wedding cake. And we have to be careful as we look in the book which plot they're presenting for us, because there are correction factors for both a two-dimensional plate, a 2.5-dimensional plate that's being pulled, or for a wedding cake that's being pulled. And so we need to understand those things. So let's look at what the book offers us as solutions. So these are the charts that are provided in the book, and we need to be careful when we use them. So there are 3 different loading scenarios that we're looking at. One is when we've got a notch, and this is the notch, and this is on chart A. The second one is when we have a hole. I think this is the more common, and not necessarily, but easier to use plot of all of them. And then this third one, C, is the stepped bar. And I'm not going to say this is not a stepped bar, this is a stepped shaft. And that's something to talk about here very carefully. I don't know what the geometry is that's being called out here. That is not clear to me. And the reason that's not clear is because I'm calling this outside dimension here lowercase d, which makes me think it's a diameter. They're doing that right there. But then, well, actually, that's the diameter of this cut. So maybe that's okay. Maybe this is a flat bar then. And the reason you say it's a flat bar is because they're using this dimension as a B and the width between the grooves as a B. If it had been a D, I would have thought it would be a shaft like the one on the end where I had a big diameter and a small diameter. Because I'm using B, maybe it's a flat plate where D is just the diameter of that groove. That's one to be careful of, and this does not do a great job of defining it. I might use a different reference when I was doing this. Now, there is a different, this chart in the middle is very different, and that is this has got a width and a diameter of the hole. This chart is pretty straightforward to use. And I think that gives us some more comfort that we're using that we know that that's a flat plate and that it's contingent, and that part of the area calculation is that thickness of the bar itself. The stress concentration does not depend on the thickness, but that's okay. So there are three charts that we can then look up, and they tell you what the important things are for how we do this. So for this first chart, we need to understand the depth of that cut and the radius at the bottom of the hole. That ratio picks which one of those four lines we're going to use. And then we look that up. We have to cross-check that with this ratio R over B. And the intersection there is going to walk us across to some value for K. So again, I've said I like this middle chart, the hole in a flat plate. That's an easier one to understand. If I've got a hole that is half the width of my plate, that is, diameter is half of the width, so that I get half. Boom, I go up, cross, and I get some ratio of, and I got to count, this is 1, 2, 3, 4, 5. So this is 2.2 with the blue line. So maybe that K would be 2.1 for D over W equal to half. That's fairly straightforward to use. Again, this last one, I think this is an axisymmetric. I think that's a shaft, but we may want to read the text to make sure that this is clear, or we may want to find another source. I've got a wonderful book. It's got about 50 pages of stress concentration charts just like this. But that's because not only are we going to use and look at these loading situations for axial loads, but we're going to have to look at these same situations with torsional loads and with bending loads. So my takeaway from this is be careful and make sure you pick the right chart. We just finished with a chart that looks like this, something like that, where I'm putting an axial load on. And in chapter 6, I'm going to get that same chart, but they're going to put a torsional load on it. And it's going to be a different chart. And the K factor is going to be different. But you could certainly drop it right in on the equation that we're using if you didn't know better. And further, this could be a flat plate, or it could be axisymmetric. Whether you do the red axisymmetric, which makes more sense for a torsion problem, or you had a flat plate, which makes just as much sense for an axial problem. Make sure you use the right chart. We're going to move forward with an example, which is going to be a hole in a flat plate. And we will also use that same flat plate with a stepped shell, with a stepped corner. So, and we'll take a look at that. And then that will also help us evaluate what really chart C is, even though I thought it was a diameter. We'll take a look at how they use it, and we'll make some further determinations. But that's our next lecture. That's going to be example problem 514. Don't worry, there's another lesson coming.